Okay, so hi everybody. In this presentation, I want to talk about the other objects in our solar system, the asteroids, the comets, the trans-Neptunian objects. Now, these objects are found throughout the solar system, but they're most concentrated in two locations. The asteroids are mostly found in the asteroid belt, which is a region between the orbits of Mars and Jupiter. The trans-Neptunian objects are mostly found in the Kuiper belt, which is found outside the orbit of Neptune. Now, the first thing I want to tell you about these objects is that these regions of space where they're found are not very densely populated. Images like this give you the sense that these regions are crowded with objects. And this leads to things like in science fiction shows where you see spacecraft trying to fly through asteroids and having to dodge them. This isn't accurate to our solar system. The asteroid belt is a location that hosts a large number of objects, but even this region is fairly empty. The number of asteroids in this region is a little hard to quantify because it depends on what the smallest object you're going to count is. But just for the sake of argument, let's just consider objects more than a kilometer across. There's about 1 million of them in this region, which is a large number of objects. But this region of space is huge. It is about an astronomical unit wide, and it's 3 astronomical units from the sun. The typical distances between objects in this region therefore work out to be between 1 million and 10 million kilometers. So most of this region is empty space. And turned out, if you don't make an effort to encounter an asteroid, you're not going to fly near one. For example, the Cassini spacecraft had to fly through this region to get from Earth to Saturn. The closest it got to an asteroid was 2 million kilometers, which means it only got a very low resolution picture of it. So spacecraft don't have to do any work to avoid hitting things when going through this region. It's mostly empty space. Even so, though, it is a region that's more crowded than usual. And this allows for a variety of different objects to exist in this region. Now, we've actually encountered a fair number of them with spacecraft that were on their way to other things or dedicated to studying these objects. These are all various combinations of water ice, rock, metal, and other things, and they're all heavily cratered, suggesting that they're basically ancient objects that have been hit by other random objects. So that's typical of asteroids. The objects in the Kuiper belt, the trans-Neptunian objects, are a little harder to talk about because the only ones we've seen up close are Pluto and Charon, and a very small object known as Erecol. There are many other objects in this region. We don't know what they look like yet, other than having very low resolution pictures and spectra. The suggestion, given what we said before about how Pluto looks to have kind of some level of geologic activity due to the fact that its surface is covered in things like nitrogen ice, which is close to its boiling point, may translate to some of these other objects. So they might have very interesting surfaces. We just don't know at the moment. So, but we do have one set of objects from this outer part of the solar system that we can encounter more frequently. These are the comets. Comets are a different class of objects. Unlike the objects in the asteroid belt, which are mainly stone and metal, these are things that contain a fair amount of ice. These are things that get into our inner solar system. And that heat from the sun causes them to basically emit particles like this picture, which is Comet Halley, which is one of the most famous of these objects. But they come from the far out parts. But since they come in, we can encounter them with our spacecraft. And we've actually encountered quite a few of them already. This one actually had a spacecraft in orbit around it, whereas most of the others were just visited briefly. What marks comets as an unusual type of object is they have highly eccentric orbits. This is the orbit of Halley's comet. This is the orbits of all of the planets. So this is Neptune, Uranus, Saturn, Jupiter, Mars, and Earth. This comet gets as close to the sun as the Earth, but it also gets as far from the sun as Neptune. This means it experiences a wide range of environments, and since it moves more slowly when it's further from the sun, it spends most of its time out here. And its characteristics are more typical of things far from the sun. Again, they're made primarily of water ice with a fair amount of other stuff mixed in. Now, these objects are typically fairly small, just maybe a couple kilometers across. But as they get in close to the sun, they start becoming what's called active. They get close enough to the sun, the water begins to evaporate. And it evaporates very strongly. It turns something that was a solid frozen ice into a gas that takes up a lot more volume. So in addition to a bunch of gas escaping, it also carries fine particles of other materials. This is conventionally called dust. Dust in Earth is a specific thing. In space, dust just means fine particles. This is one of those comets. This one is what had a spacecraft in orbit around it, and you can see that material beginning to emerge as it's getting closer to the sun. Now, this stuff, this fine debris from this 10-kilometer object spreads far and wide because this thing has very low gravity. As an object like this approaches the sun, that dust spreads out, forming what is called a coma. And while there's a 10-kilometer wide object in the center of this dust cloud, these dust clouds can be comparable in size, not just to planets, but to the sun. There's much less material here than in the sun, but this object is something we can start to detect. A 10-kilometer wide object is really small and really hard to see. A fuzzy dust cloud that's like the size of the sun across, that's much easier to see. And as these things get even closer to the sun, that dust doesn't just form a cloud around the nucleus, it gets stretched out into tails. When they get close to Earth's distance from the sun, the sunlight and the solar wind interacting with that gas and dust starts to pull that material into long tails. These tails are truly enormous structures. There isn't much material in this. This is all stuff from a few kilometer wide object, but it's stretching over distances comparable to the distance between the Earth and the sun. In these tails in very spectacular comets are enormous. They contain very little material, but because they're so big and they are fairly good at scattering light, they become one of the most dramatic things you can see in the sky. And it's all coming from a tiny little object just a kilometer across, which is the typical size of small asteroids, etc. So these are, of course, interesting objects. People have been interested in them for a while. And what's nice is, since there is so much stuff coming off of them, we can actually get senses of what they're made out of. This is how we know they're made out of water and other things. You can measure the properties of this stuff because it's fairly bright. But why do we care about these little objects, these things that are maybe a few to a few hundred kilometers across? Well, there are practical reasons and scientific reasons. On the practical side, which is the one we're going to focus on in this particular video, there is the fact that these objects are a risk. There is a chance that they could hit us, which is not a good thing, and do damage. There are also people who say that these could be potential resources. Since these objects don't have much of their own gravity field, it'd be relatively easy to take material from these objects, which is common, which has a lot of metals and other materials that are quite valuable, and bring it back to Earth. Whether that's economically viable or not is kind of an open question. On the scientific side, the reason these objects are interesting is that they are bits from various parts of the solar system, which come close to us, so that makes them helpful. Also, they turn out to be relics of the early solar system and so provide information about how the solar system formed. That'll be the particular focus of the next presentation. For this presentation, though, I want to focus on this hazard statement because it is a good reason to care about these objects. And this risk has been brought into sharp focus thanks to an event that happened in Chelyabinsk, a town in Russia, back in 2013. This was when an asteroid, a fairly small one, collided with the ground. This was something that was seen in lots of video cameras. It was something that came down, exploded, produced a big explosion in the air that damaged buildings, broke windows, hurt a few people, and then landed on the ground. This gives a sense that there is some risk associated with these sorts of events. That some of these small objects can, in fact, impact Earth. And they don't just impact Earth, they impact all of the planets. We have actually seen objects crash into Jupiter. A comet tore itself apart and then crashed into Jupiter, producing these impact scars. We've even seen more recent impacts. The last one happened just a few weeks ago, producing a bright flash. There's even evidence in Saturn's rings that things have crashed into them. We already talked a bit about that. So we know objects can crash into planets. This is different from the solar system we often think about. If we think about just the planets and even fairly big things like, say, Pluto, these are all things on nice, relatively circular, relatively well-spaced orbits. These objects are never going to run into each other. And people have done careful numerical studies of this. They go, oh, could this ever happen? And the chances of any of these objects by some weird gravitational interaction ever colliding with each other is a very low probability event. This is a very regular, stable system. The motions of the small bodies are not nearly as well behaved. There are small bodies that get all the way into the orbit of Mercury. There are objects crossing all of the planet's orbits. This is a map, again, space is mostly empty, but this shows every object we know about. And they're on trajectories that can potentially hit all of the planets. How does this happen? You would think if something could have hit the planet, it would have hit a planet by now and thus be gone. It's been 4.5 billion years. Why haven't all of these things been destroyed? Well, the reason for that is because it's easier to move the orbits of these small bodies compared to the orbits of planets. There are a variety of processes that can allow the orbits of small bodies to change. One way it can happen is just two of them run into each other. This is a cool image of an asteroid called P2010A2, which exhibits a comet-like tail, sort of. But if you look closer at it, that tail isn't just a bunch of debris, it seems to form an X-like pattern. The implication here is two objects crashed into each other and knocked material off each other, producing the debris. That sort of collision will also change their orbits a bit. Maybe not by much, but by some. It also turns out that just sunlight can change the orbits of these guys. The way that works is the following. Imagine you had an asteroid spinning here. Now, that asteroid will heat up on the side that faces the sun. But if it's spinning, that hot side gets rotated a little bit this way. So that produces thermal radiation that comes off preferentially on one side of the object. That acts like a little bit of a thruster, not a very efficient one, but over time, it can cause the asteroid to basically speed up or slow down, depending on which way it spins, which can affect its orbit. Now, these sorts of processes won't change the orbit very much, but there are certain places in the asteroid belt where changing the orbit a little bit is important. These are regions known as the Kirkwood gaps, which can be seen in a plot like this, which shows the number of asteroids as a function of distance from the planet. What you will notice here is there are several locations where there aren't any asteroids, like right here at 2.5 AU and right here at about 2.82 AU. Those locations are caused by mean motion resonances with mostly Jupiter, but also other planets. This distance, we're in the 3-to-1 resonance. So the asteroid would be going around the planet 3 times every 1 time Jupiter goes around. Here the ratio is 5-to-2, there's something happening at 7-to-3, and here's 2-to-1. As we talked about in the previous presentation, resonances can perturb orbits. Take an orbit that's initially circular and avoids all of the other planets and give it a significant eccentricity. Since Jupiter is really massive, it's good at doing this. And so if you have an orbit that starts just outside of the Kirkwood gap and pushes it into that gap, all of a sudden its eccentricity will grow. It will start having an orbit that oscillates back and forth and gets closer and further from the sun, getting it onto orbits that can cross the orbit of Mars or Earth or Jupiter. So that combination of slow evolution and then resonant interactions can throw asteroids into the inner solar system. Now, comets are a slightly different story. Comets and objects like them come from the outer part of the solar system, the Kuiper belt and the Oort cloud. These are far from any of the other planets. So there's not a lot of ways to perturb them onto things that would come into the inner solar system, at, at least not from the other planets. The thing is, the Oort cloud in particular extends so far from the sun that the gravity of other stars is relevant. As other stars pass kind of close to the sun, it can change the orbits of these objects far from the sun, allowing them to fall into the inner solar system. And if as they're coming in, they have a close encounter with one of the planets, say Jupiter, that can torque the orbit and put it on something like the orbit of Comet Halley, which oscillates back and forth between the inner solar system and the outer solar system. So there are processes which can take small bodies and throw them into planets. We want to care about this because these sorts of collisions can potentially do damage and can have practical ramifications. The most dramatic is one of these events ended the age of the dinosaurs, at least the giant dinosaurs. But we have more kind of readily available senses of how much damage these can cause. Small bodies don't do too much damage. For example, this is the Park Forest meteorite, which was an object about this big that crashed into a location in suburban Chicago. Didn't do too much damage, just punched a hole. Thus far, nobody has been killed by a meteor that we know of. Somebody got their leg broken. That Chelyabinsk meteor was bigger. It's more like 17 meters across, which is, pretty substantial. But what it did when it hit the surface is just punch a hole in a lake. If this had happened in like a major city, this would be probably a bad thing, but it's fairly localized. Bigger objects do more damage. And there's kind of a critical threshold where we start to care. For example, this is Meteor Crater. It's a kilometer across. This was a damaging event. If this had happened over a populated area, whether there were any people to see this is another question, this would have done major damage. Now, based on those previous pictures, you might go, okay, this requires something a kilometer across to produce this hole. That's not the case. The size of the object that produced this thing was probably less than 100 meters across. So going from 20-ish meters to 100-ish meters makes a major difference in how much damage it can do. Now, why is that? Well, to understand this, we have to go back to that basic principle we talked about earlier, which is conservation of energy. Remember what we said is energy is one thing that is assumed to be conserved in physics. One form of energy is motion. Anything moving carries kinetic energy. Anything else can be regarded as a potential to create motion. Now, to be a little more explicit about that, the actual energy carried by a moving thing is given by a fairly simple formula. It's 1/2 times the mass of the object, so how many kilograms it has, times its speed squared, 1/2 mv squared. That is the actual numerical value of the energy carried by something moving. Now, when an object hits something else, that energy has to go into other forms. That can be in the form of sound, heat, light, breaking things, etc. And the thing about asteroids and comets, they are moving very quickly when they hit us. The Earth moves around the sun at a speed of 30 kilometers every second. That is faster than anything we have experience with. Even bullets only go at speeds up to about 2 kilometers a second. This means that if an asteroid hits us, it's coming at a very high speed. Carries a lot of kinetic energy. Now, you might say, well, how fast can it really hit us? Well, it depends on what angle it hits us at. You can get speeds up to twice Earth's speed around the sun. That's 60 kilometers a second. But there's also a practical lower limit to the speed. Even if something is approaching the Earth very slowly, Earth's gravity is going to pull it in. And it turns out that just that alone will cause the object to be moving at 11 kilometers per second once it gets to the top of Earth's atmosphere. So these objects coming in are moving fast, so they carry a lot of energy for their mass. Now, what happens to that energy does depend on the size of the object. If it's a small object, like the Park Forest meteorite, it's slowed down by the atmosphere. That energy goes into heating the atmosphere and slowing the object down so that when it actually hits the surface, it's moving at a more sensible speed of 100 to 200 meters per second, enough to dig a small hole but not do too much damage. The Chelyabinsk meteor also did this. It slowed down to the same sort of speed before it hit the lake and made this hole. But as it came down, it was transferring more energy into the atmosphere because of its higher mass. That energy deposition in the atmosphere created this bright flash. It also created shock waves that broke windows, and hurt people who happened to be standing by those windows. As you make your object bigger, this becomes more and more important. The most famous example of this is an event that happened in 1908 in Russia called the Tunguska event, which is thought to have been produced by a similar process, just involving a somewhat larger object. In this case, an object, probably something relatively low density, was flying through the atmosphere and basically dumped all of its energy into the atmosphere, producing a major what's called airburst. This dumping of energy produced a shock wave that knocked over trees, set fires, and damaged areas. This would have done a lot of damage if it was close to a populated area. Fortunately, there weren't many people very close to here. So this sort of object could have done significant damage. Now, if the object is much more massive or bigger than that, so remember, objects could be comets and low density or more rock or metal rich. So what really matters is the mass. If the mass is above about 10,000 kilograms or about 10 tons, the atmosphere isn't able to slow it down. So the object hits the surface at kilometers per second. That dumps a huge amount of energy into a small part of the Earth's surface. That material has to release that energy somehow. What happens is more like an explosion than a digging. Basically, you have dumped a whole bunch of energy into a small volume. That's what an explosion is. Basically, material gets thrown out of the region, forming a crater. And also material gets moving, which creates earthquakes and further reinforces the crater. The size of the explosion determines the size of the crater. And it works out that the crater you make is typically 10 times the size of the object that produced it. So, and this has been studied in detail for a couple of different impacts. On Earth, meteor crater is one good example. Since it's a well-preserved crater, we have a sense of what it was. It turns out it was probably a metal-rich object, which meant it could be a little smaller. Its mass was about 2.5 times 10 to the 8 kilograms, and it probably hit the Earth at a speed of about 12 kilometers per second. This is equivalent to, for those of you who like explosive statements, 10 million tons of TNT. This was a very powerful explosion. The other useful baseline for comparison is, of course, the impact that marked the end of the age of dinosaurs, which we know happened in Mexico, happened at the edge of the Yucatan Peninsula. If you look at topography, you can actually see the edge of the crater subtly here. If you look in gravity data, which is actually a better way to do it, you can see the rings of the crater here. This crater is about 180 kilometers wide and was created by an object maybe 10 kilometers wide. So about 100 times bigger than the object that produced meteor crater. The thing is, realize mass goes like 100 times 100 times 100. Mass goes like volume, not like diameter. So there was 1,000,000 times more energy in this event. This is why this event affected life on Earth to a significant degree. Now, of course, other things were going on. There were volcanisms, etc. How much this was just wrapping up things versus, really damaging life as we know it on the entire planet is still a matter of discussion. But this event would have released an amount of energy equivalent to 100 million megatons of TNT. To put that in perspective, all nuclear weapons currently available on the planet Earth that we know about are 10,000 times less than that. This would be bad if it happened to us. So we do want to know what these sorts of things are around. What are the risks? Which are there objects 10 kilometers across that might hit us? We definitely want to know about those. We also want to know about objects in the 100-meter range, because those could do significant damage. And for that reason, people are seriously making an effort to find all of these objects. This is a plot from a report done a few years ago, about 10 years ago now. What you're seeing in red is basically the total amount of objects discovered of different sizes. So this is a number of objects as a function of size. And these are, again, logarithmic scales. So here is 10 kilometers, which corresponds to the things that might have ended the age of the dinosaurs, which are very powerful events. We actually have found pretty much all of these objects. We know where they are. We know whether they pose a risk or not. They don't. As we go to smaller and smaller objects, the number of objects goes up. There's more small objects than big ones. Great. As we get to and we've gotten most of the objects down to about a kilometer or so. Beyond that, it's very hard to see them because they're small and faint. These are the sorts of objects we want to find because these are the ones that can do Tunguska or Chelyabinsk level destruction. Now, Chelyabinsk didn't do that much. Tunguska could have done quite a bit if it happened over a habitable area, a densely populated area, but this gives a sense of how much work we have left to do to find all the potentially hazardous objects out there. And it's a reason to keep looking because there are quite a few of these objects still to be found. And with that, I'll wrap up this particular presentation and thank you for your time and attention.